So we need to make sure that when the camera rotates, when we are filming the 20-metre sprint, that the camera will be rotated from the left to right in order to follow the movement of the participant. We need to make sure the camera is not angled and so it remains flat when it's rotating. This is also related to the pan, which is the ability to move the camera from left to right. You measure an athlete moving from one position to another, so it is important that this is checked prior to the investigation to make sure that the camera is in fact in the right place in order to capture all the motion consistently. By counting for the physical setup with the camera helps to combat the idea of perspective error, and this is something that biomechanists should be aware of, as it can influence the results, making them skewed and therefore inaccurate. Perspective error is where something can appear different in terms of its size to what it actually is in reality. For example, when looking at something close to us will appear larger, but that same object when placed further away will appear much smaller. So if the position of the camera or the person within the field of view plays an important role, as it can produce results that are misleading, because at different angles, if you stand face on or at a slight angle, it will produce different results than standing perpendicular. So when conducting the 20-metre sprint test, we must be mindful of the data being produced at the 0, 5, 15 and 20 metre marks, because we are not standing perpendicular to those cones, so the only true result will be at the 10 metre mark, because we are standing perpendicular to the plane of motion, and therefore the other cones will be skewed with the potential of having perspective error. So in terms of the ideal method, as we've said, force plates are the ideal way of measuring force in a biomechanics lab, and light gates for measuring 20-metre sprint tests or other sprint tests. But as we're going to mention, we don't actually have access to this due to the current period at the moment, so we're going to have to manipulate our data collection to try and make it as standardised as we can. So moving on to our version of how we're going to conduct it. As we've mentioned, we are unable to carry out the appropriate fitness tests and to use those methods, and we don't have access to the high-tech equipment. So instead we're going to be using 2D cameras as opposed to the Vicon ones when conducting our data collection. When using 2D cameras, we must be careful when structuring capture. As an example is a bowler may miss certain when they're bowling. When you're filming, you may miss certain body parts, so ideally we would need 3D imaging for complex skills, but due to Vicon cameras being very expensive, we don't have access to them. So firstly, it is important to note that when collecting data, the setup of the 2D camera is vital to take the time to prepare. Set up accurately so it doesn't influence the overall results, and it can take a long time, but this is to make sure the results are not skewed. It is important that planning has taken place beforehand to make sure that when filming the vertical jump, the participants remain within the field of view. So by being aware of the field of view will prevent not capturing all the movements. A way of preventing skewed data is by practicing before the experiment to see if the settings are right and the position of the camera, so if they are not, they can be modified before the investigation takes place, so that we can actually concentrate on collecting the data when we're carrying out the investigation, rather than trying to adjust the setup midway through the practical. When deciding on where to place the camera, some considerations that should be taken are the plane in which the motion is being performed, the distance you are filming from the participant, which will vary depending on the skill being observed. As for example, if you are observing a basketball layup, you're going to need to be further away from the participant than you would in a golf swing to make sure that all the motion being performed is captured within the field of view. This is going to be important when we carry out the vertical jump, which is more isolated than 20-metre sprint, so we would normally position ourselves at a perpendicular angle to the participant, which will be possible in the jump, but not in the 20-metre sprint. We're going to collect data on the 20-metre sprint tests, as in a basketball player's running speed is very important for basketball players. There will be a series of cones marked out at each 5-metre intervals, so in total there will be 4 cones. The performers will start from behind the first cone with 1 foot up to the line and be counted down from 3, 2, 1, and then timed on how quickly they can run from the first cone to the 4th. We're going to be using our phones as a stopwatch to record when the participant passed through each of the cones to know their times at each 5-metre interval. And on another phone we are going to record the participant as they sprint from the first cone to the last. The reasons why we conducted the collection method this way is because the equipment used for elite athletes, as we've said, we don't have access to them. So we've had to modify these tests in the most effective and standardised way that we can to gain accurate data. But we are aware that light gates, instead of using a stopwatch, and cones is a more professional and scientific way to gather data. We're also going to collect data on the vertical jump to measure the power and height of the basketball performer's jump by using a camera to collect these readings. After this, we will then analyse the performance using software to determine the biomechanical aspects of the skill against the perfect numerical model. We are aware that we can use specialised equipment like force plates when collecting data to gain more detail and accurate readings, but we do not have access to them. So instead we are going to be using a vertical jump mat where the participant will stand on the mat and will wear a belt around their waist which is connected to a measuring tape and connected to the mat. Before jumping, the participant's mass in kilograms and height in centimetres will be recorded, and they will need to make sure the string from the belt connected to the mat is taut and the tape is calibrated to 0. Otherwise, this may affect the results by not giving a valid reading, which will compromise the reliability. After this, the participant will swing their arms down by their side and bending their legs at their knees to create this counter movement, to then extend their legs to jump in an upwards direction. They will then land back on the mat with their knees bent. The reading is then measured from the athlete, and they will complete 2 jumps, and their best score will be taken. While the participant is participating in the vertical jump, we will be recording the footage on our phones, being positioned at a perpendicular angle to the participant, as all the motion is occurring in the sagittal plane. Otherwise, if the camera is not set in that direction, the data will be skewed and not an accurate representation. We are going to use our phones to record the data, but we know that a high-speed camera in a lab would be more scientific and a better way to measure the data collection, as it can change the sampling frequency, shutter speed, focus and iris in order to capture every part of the movement. You would want a high sampling frequency which takes lots of small images, which captures the small details that can be missed when using a phone. And on our phones we understand that the picture will perhaps be less clear, so it's extremely vital, especially for elite performers, that high quality cameras are used. However, if we follow and make sure that our cameras on our phones are set up correctly at the right distance and angle from the participant to make sure they are within the field of view, we can still obtain data with a degree of accuracy. So now we're going to analyse the data we collected from the 20-metre sprint test results. And we've collected data on a better BASFIC basketball performer and our chosen performer, who's perhaps slightly weaker. So if we first look at the distance time graphs, we can see for our chosen performer that from 0 to 2 seconds they covered a distance, in 5 metres it took them 2 seconds to complete 5 metres, compared to the better performer where it took them less than 1 second to achieve 5 metres. So instantly we can see that our chosen performer it took them much longer to achieve that distance. Then we can see that from 5 metres to 10 metres they accelerated much more quickly, so it only took them around half a second to actually achieve 5 metres. This may have been factors like it took them longer to sort of get into the motion of the sprint test and to accelerate. And then we can see that they progressively accelerated again from 10 to 15 metres, and then we saw a sharper increase from 15 to 20, which only took about less than half a second for them to achieve that 5 metres. Compared to the better performer, where they consistently sustained their time to complete the distance, so we can see that they pretty much went up by half a second each time, and they completed the whole sprint test in under 3 seconds, whereas the chosen performer took them over 4 seconds. So we can see clear differences here. This also may have been a result of their inertia, which is related to Newton's first law. They may have had a larger mass than the better performer, which then therefore required more acceleration for them to achieve the distance in the same time as the better performer. So this may have affected them, and therefore it took them longer to accelerate because they needed to generate a larger force. In terms of the velocity time graphs, our chosen performer, we can see that it took them less than 2 seconds to achieve a velocity of 3 meters per second. You can see that they are definitely accelerating because the gradient of the graph, it's not a very steep gradient, but it's sort of a constant. Then we can see a steeper incline, so they're accelerating, they're speeding up, and they achieve from 3 meters per second to about 5 meters per second. And it took them about 1.5 seconds to do that. Then we can see that the line slightly plateaus, so they sort of sustain the velocity from 2.5 seconds to 3.5 seconds. And then we see again a sharp increase from 6 meters per second to 9 meters per second in space of half a second, so they sped up at the end of the race, compared to the better performer, where they accelerated quickly, really quickly, a steep gradient they went from 0 meters per second all the way to nearly 7 meters per second in less than a second. So they really accelerated quickly at the start of the race. They maintained this and managed to increase their velocity from 6 meters per second to 8 meters per second. And then we sort of see their speed begin to plateau. And then at the end, from after 2 seconds, they increase at the end of the race their velocity from 8 meters per second to 10 meters per second. You can see that the better performer reaches their peak velocity at a faster rate than the chosen performer. They reach 7 meters per second before 1 second, whereas the chosen performer only reaches 3 meters per second, and it nearly takes them 2 seconds. So this is all to do with their acceleration. As we've said before, they may have to input more force in order to produce a greater acceleration, and therefore it may have taken the chosen performer slightly longer to accelerate, which is why we see at the end it suddenly shoots up the steepness of the line, compared to the better performer, which manages to sustain their speed and velocity all the way to the end. So we can see clear differences there. And in terms of acceleration, we can see with the chosen performer, it takes them quite a long time to actually accelerate. They don't actually start accelerating until around 3.5 seconds. And they're only actually doing 0.5 meters per second squared. So they're not actually accelerating very much until the end of the race, when they finally increase their acceleration to 6 meters per second squared. So we can see at the start there is quite a slow increase in their speed. They're not reaching their peak velocity. They're sort of maintaining this sort of steady pace, and they do this pretty much throughout the whole race until the end. Whereas if we look at the better performer, they reach their peak velocity almost instantly. It's around 8.5 meters per second squared before 1 second. However, they can't sustain this, and therefore the acceleration drops to around 2 meters per second. So it's quite a large increase, slowing down. And then they slow down further again to 1 meter per second, and then manage to regain at the end and produce an acceleration of 3 meters per second. So we can see that although they meet their high peak velocity power, even the better performer, they're not being able to sustain it. And that is what we want to do when we're participating in our sports. We want to be able to sustain this power for the whole time, to maintain this and not to fatigue. Otherwise then we're going to see a deceleration, which will affect our performance. Chosen performer may have taken more time to accelerate because of the action-reaction forces. They may have not applied as greater force onto the ground, so then wherefore when they tried to accelerate from the starting line, they found it really difficult to reach their maximum peak velocity at the rate that the better performer did.